This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right. Can you hear the buzzing sound? I don't know why. I'll just use this anyway. All right. Okay. I think we should start. So welcome to week 3. All right. And week 3 is where things start to get a bit more exciting. Alright, so the F4 lab starts this week. How many of you have been to the F4 lab today? There should be, I guess, 12 of you. Did you all enjoy it? Yay, meh, nah. Alright, so please go to your allocated F4 lab schedule, alright? So there's only 6 people in one lab session. So if yours doesn't start this week, it might start the following weeks, right? So just keep in mind. So please wear covered shoes and dress appropriately and be on time, okay? So if you come late, chances are all your group mates have gone into the lab session and you might be left outside. So please be on time, okay? So I have a short video, basically, to give you a bit of background, what kind of research is going on at the Walter Bassett Aerodynamics Lab, right? And hopefully this will spur your motivation, will spur or motivate you when you're doing your F4 labs, all right? So let's have a look.
Up to half the cost of a plane ticket is fuel. And most of the fuel is to overcome drag. What savings could be made if drag could be reduced?
If we could reduce the fuel bill on an aircraft by 10%, that would work out to about $15 billion a year in fuel cost savings globally. So it's a huge number.
Engineers are on the case, studying flow around wings. In this water tank, red dye goes over the wing, green dye under, revealing the flow downstream in full and beautiful detail.
With this setup, you can actually see what happens when an aeroplane stalls. At the moment, we've got a nice smooth flow over the top and the bottom of the wing. But if you increase the angle of the wing, the angle of attack, you can see that flow just breaking up a little bit there. And all of a sudden it separates away from the top of the wing, it's stalled. Next thing is, the plane plummets out of the sky.
But this kind of smooth flow, laminar flow, is not what produces much of the drag. Rather, it's caused by an invisible skin of microturbulence around the plane. You can see this turbulence by putting a rod in a smoke-filled wind tunnel. Upstream, the flow's smooth, laminar. But downstream, the whirlpools and eddies of turbulence are clearly visible. These cause drag. Turbulence is not just associated with flight. It's very common throughout nature. It's there whenever the wind blows or the ocean flows. Indeed, turbulence's drag is vital to our world. It'd be a very different place if all flows were smooth laminar lakes.
For example, if we looked at the Yarra River and we assumed it was just a laminar flow, so sheets sliding over each other, and you did a quick calculation, the speed of the Yarra River would be 20 kilometres per second.
That's 72,000 kilometres an hour. There'd be no Yarra River without turbulence.
We've been working on it for over 100 years, and still we have very limited knowledge or understanding of the turbulent processes.
So, to study it in unprecedented detail, over 14 years, Melbourne University engineers built a very impressive wind tunnel dedicated to reducing drag.
Now this is the opening of the wind tunnel. Air is drawn in through here via the giant fan. But what happens on the other side is the key.
The air passes through a series of baffles which gently turn through a 180-degree bend. Then a series of meshes make the flow completely smooth, ready to enter the impressive working section of the tunnel.
What makes our tunnels unique is we have a working section which extends over 27 metres. That's much larger than any other wind tunnel in the world for this flow quality.
Turbulence is not a random mess like it might appear. A sheet of laser light through the flow reveals the patterns.
I guess the motions within that layer, everybody used to believe that they were quasi-random. It's repeating patterns or features within that turbulence that we can learn about, and if we can learn what those features are,
So that's Nick.
we can learn to control them.
Professor Nick now.
Control them and drains reduced. This might be done by putting tiny actuators over the outside of the plane to subtly change the flow.
So the actuator can be tiny flaps that pop up from the surface, or it could be microjets that pulse in such a way that you're going to destroy those turbulent eddies close to the surface.
Another way to reduce turbulence is to take inspiration from nature. Dolphins can swim faster than expected because of vibrations in their soft, flexible skin.
It's believed that what happens there is that you get a travelling wave set up in the skin of the dolphin, in a way, again, interacting with the turbulent flow, which producing conditions where they can travel at much higher speeds as to if it was simply a solid, rigid surface.
But the easiest animal for us to copy is the shark. Its skin is stiffer, but less smooth.
If you were to rub the surface of a shark, it will be particularly rough in one direction and not in the other. So there's definitely a textured surface to it.
Here's the close-up. This textured skin has evolved to minimise turbulence.
Through methods that we don't entirely understand, it somehow manages to reduce the turbulence close to the surface of the shark and hence reduce drag.
One day, the outside of aeroplanes may resemble shark skin. Here's one of the surfaces they're planning to test. Now it's covered in a whole lot of very fine ridges. They're less than 0.5 millimetre apart. And they're set up in quite an interesting way. Here, they tend to push the flow, or in this case my fingers, together. Here, they push it apart. Now they're going to lay a whole lot of these tiles in the wind tunnel. By testing different groove arrangements, they hope to find the one that best reduces drag. It's early days yet, and researchers are just starting to unlock some of turbulence's complex motions. But the results from this incredible new wind tunnel will emerge over the next few years.
Alright, so hopefully all of you are inspired and excited to do your airfall labs. Right, so that wind tunnel is one of the wind tunnels in the Walter Bassett Aerodynamics Lab, but the ones that you'll be using will be a bit smaller than that, alright? But when you walk into the lab, you should see this big wind tunnel on the right-hand side. Okay, also this week MATLAB workshop starts and tutorial starts as well. Okay, alright, so just I guess a brief recap of what we did last week or on Thursday. So we investigated this flow where we have a source and a uniform flow, and we wanted to I guess kind of sketch what the flow field would look like for this source and uniform flow right? So the first thing hopefully you all remember is that you have to write down your stream function for this flow, where psi is just equals to your uniform flow plus your stream function for your source. Okay? Right, and we then differentiate our stream function to obtain our velocities u and v, and that's important because we want to find out where the stagnation points are in this flow. Okay, so to find the stagnation points of the flow is basically just setting when our velocities u and v are equal to 0. Right? Okay, and if you do a bit of the maths, you'll see that your stagnation point occurs along the x-axis, right? and the streamlines which goes through your stagnation points are going to be your separatrix. Okay, so to find the equation of the separatrix, all you have to do next is then substitute your location x and y of the stagnation points into your stream function, and that will give you a value for psi. Right? In this case, psi is equals to 0 at the stagnation point. And what I do next is substitute that value of psi back into my stream function. Okay? So if I rearrange it, I then get an equation for my separatrix. Okay, and from this equation here, hopefully you can see that one possible solution is when y equals to 0, right? Now, if I rearrange the equation of my separatrix so that I have x as a function of y, u infinity, and qs, I can then get my other separatrix, right, which is this curved surface here. Okay. So to sketch this flow, I needed a few more extra information. So I wanted to find what's the y location when x goes to negative infinity, and also what's the y location when x approaches 0. All right. So just a few more points to help me sketch this flow. So when x approaches negative infinity, okay, this denominator term here has to equal pi. Okay, and I'll get y equals to plus minus qs over 2 infinity. Now, some of you ask me, why is it pi? Why can't it be equals to 0? Right? Why can't that term, this term here, equal to 0 instead of approach 0 instead of approaching pi? So I've added a bit of notes, right, in last week's write down. So keep note that we want x to always approach negative infinity, all right, and that only occurs when 2 pi u infinity y over qs approaches pi. Okay, and that's because when this term here approaches pi, okay, the tangent of that term approaches 0 from negative. Okay, does it make sense? Right, so if I do a check, right, so this is my equation of my stream of my separatrix. Now, if y is positive, but my tangent term or my denominator is approaching 0 from negative, okay, therefore my value of x has to be negative, which is what we want, right? We want x to approach negative infinity. Okay, and I guess I confused some of you because in my solution here I wrote plus minus, right? Y plus minus qs over 2 infinity. So this term here can approach pi and can also approach negative pi. Okay, and that's why I have plus minus for my y value here. Okay, now can anybody tell me why this term cannot approach 0? Why? Because if I make this term approach 0, right, you'll find out that x doesn't approach negative infinity. It actually approaches infinity, right? It approaches infinity instead of negative infinity. Okay, if you don't trust me, you can try and substitute that as 0, and you'll find out that y approaches 0 when this term here approaches 0, right? Which is basically you're approaching your stagnation point. Okay. Right, and also this solution here, there's someone who asked me, isn't the solution pi plus 2 pi n, right, where it can be multiples of 2 pi. Yep, that's true, but in this case, we're only taking the smallest value right? Which is just pi and negative pi. Okay, does that clear up a little bit? Or you guys weren't wondering about it at all?
I don't think there is a difference between 0 and pi.
0 and 1?
Pi.
0 and pi?
Yeah.
Try and substitute 0 into here. Then you get y equals to 0, right?
Yeah.
But if you remember from the notes,
Y equals 0 is
yeah, your stagnation point. So yeah, so you're approaching infinity instead of negative infinity. Okay. Right. So that's that for when x approaches negative infinity. The next thing which I wanted to do was then to find when x approaches 0, which is quite easy. So all I have to do is just substitute x equals to 0. Okay, and you'll see that y is equals to plus minus qs over 4 u infinity. Okay, so it is very important that you know how to sketch these flows. Okay, so once you've found your equation of stream function and your velocities, okay, you then need to find your stagnation points. Okay, and remember that your stagnation points is a saddle point, right? Basically, you have two streamlines entering it and two streamlines exiting your saddle points, your stagnation point, right? From that, I can then sketch my separatrix. Okay, and to sketch this flow, you should know that when you are considering the flow close to the origin, which is where your source is located, the flow features there is going to be your source, is going to be dominated by your source, right? So basically, if I have a look here, okay, regions close to my source is going to look, is going to be radiating all outwards, right? It's going to look like a source, okay. Okay, and in the far field, I'm going to have my uniform flow, which is going to dominate. Okay, so at regions away from my source, I'm going to have uniform flow. Now, very, very important, your streamlines cannot cross. Okay, and your adjacent streamlines must flow in the same direction. Right? Do you all understand that? Right. So you can't have a streamline which looks like that. Okay, that means you have done something wrong, okay, in your drawing, and you can't have a streamline where one is going to the left and one's going to the right, or in the opposite direction. That doesn't work as well. Okay, so these are a few sanity checks which you can do. Right. Now, what do we know about streamline? What's the velocity perpendicular to the streamline? Zero, right? So velocity perpendicular to a streamline is 0. Therefore, I can actually replace my streamline with a solid boundary. Okay? So in this case, I'm going to replace my curved separatrix line with a solid boundary. Okay? So I'm just going to replace it with a solid boundary. Okay, and this geometry is known as a half Rankine body. Okay. Right, so remember our ultimate goal is to find the, to know how a flow over airfoil looks like, right? And we want to also investigate the forces acting on the airfoil. Right, so we want to find the pressure distribution around this half Rankine body to start with. Okay. So how can we find the pressure acting on the surface, right? And can we apply the Bernoulli's equation? Right, so let's consider our Euler's equation for a two-dimensional inviscid and incompressible flow. Okay, let's do this together. Okay, so I'm going to write down my Bernoulli's equation, my Euler's equation. So I hope all of you can write this by heart now, right? You should know how to write your Bernoulli's, your Euler's equation. Oops. I can't copy it. Anyway, write it again. Del V del T plus V. Okay, so this is your Euler's equation. Now, we're going to derive our Bernoulli's equation from our Euler's equation. So what we want to do is we want to take our momentum equation in the x direction, okay, and we want to multiply it with dx. Okay, and I'm going to take my momentum equation in the y direction and multiply it with dy. Okay, and I'm going to call this equation 1. And this one here, equation 2. Okay, I'm just going to write down what I said. So, multiply okay, so there's an assumption which I'm going to make. So I'm going to assume that the flow is steady as well. Okay. Okay, and the next thing I'm going to do is I'm going to add equation 1 and 2 together. So, if I'm assuming steady flow, which terms do you think I can cancel off? The first term, right? Anything which has del t inside, right? So my time derivative can be ignored. Okay, so so the next step is I'm going to combine these equations. So I'm going to get u, should I do this? Yep. Del u over del x dx plus v del u over del y dx plus u del v over del x dy plus v del v over del y dy. That's going to be equal to negative 1 over rho del p over del x dx minus 1 over rho del p over del y dy. right? So what I'm going to do next is I'm going to factorize this equation. So I'm going to clump my u together. I'm going to clump my v terms together as well. Okay. So then I get u bracket del u over del x dx plus del v over del x dy plus v del u over del y dx plus del v over del y dy. Okay, and that's going to be equal to negative 1 over rho del p over del x dx plus del p over del y dy. Right? Is that correct? Looks okay? Now, we can simplify this equation a little bit, okay? And what you're going to do is we're going to assume irrotational flow. Okay, so irrotational flow basically means that zeta is equal to 0, okay, which hopefully you know that zeta is just the Laplacian of psi, okay. Okay, so the Laplacian of psi is just my vorticity, right? So therefore it means that del u over del y equals to del v over del x. Everyone agree? Yes? Right? Because we know that vorticity, or the Laplacian of psi, is just del u over del y minus del v over del x, right? So I just brought it to the other side. So I get del u over del y equals to del v over del x. Okay? Now, this is important because what I'm going to do now is I'm going to interchange this term here, del v del x, right? And I'm going to interchange it with del u del y, right? And I can also do it with this term here, del u del y. Okay, I can interchange it with del v del x. Can you all see that? Okay, so I'm gonna change it. Oops. Okay, so I should get u now equals to del u del x dx plus del u del y dy plus v del v del x dx plus del v del y dy equals to negative 1 over rho del p del x dx. plus del P del Y dy. Okay? Now, this is good because I hope all of you can see that this term here, oops. Can anybody tell me what this term is? Du. Very good. So that's just du. Okay, and this one is dv. And this is dp. Okay, so I'm going to rewrite this as, oops. So basically what I end up with is just u du plus v dv equals to negative 1 over rho dp. Okay, so it simplifies to this equation here, and I want to integrate this equation between two arbitrary points, right? Just any arbitrary point. So integrate between points 1 and 2. Okay, so these 2 points 1 and 2 are just arbitrary, right? It doesn't have to be along a streamline or anything. It could be anywhere. Okay, and integrating that is quite easy, hopefully. Alright, so you should get 1 over 2 rho u1 squared plus 1 over 2 rho v1 squared plus p1. Okay, and that's going to be equal to half rho u2 squared plus half rho v2 squared plus p2. Okay, so basically what I've done, I've just taken the 1 over rho over to the other side and I just integrate it and I just rearrange it so that all the 1 terms are on the left and the 2 terms, the 0.2 terms for 0.2 are on the right. Okay, and we know that that is then equal to a constant. Okay, so this is the Bernoulli's equation for irrotational flow. And is applicable anywhere. Okay, so your Bernoulli's equation is valid everywhere in the flow field, okay, for an irrotational flow. Okay, everybody is following so far? Right? Any questions? Now, do you all remember how we derived the Helmholtz equation? Okay, so Helmholtz equation, we also started off with our Euler's equation, right? But hopefully you don't get confused. Okay, so in the Helmholtz equation, we differentiate our momentum equation. Okay, with respect to y. Sorry, we basically differentiate our momentum equation in the x direction with respect to y, and we differentiate our momentum equation in the y direction with respect to x. And what we do is we then take one equation and minus off from the other to get rid of the pressure terms. Okay, but when we are deriving the Bernoulli's equation, we need these pressure terms, all right? So we take the x momentum equation and multiply it by dx, and y equation multiplied with dy, and we sum them up together. Okay, so don't get confused, all right? In the exam, if they ask you to derive the Bernoulli's equation, don't derive the Helmholtz equation, right? So it goes back to, again, understanding these equations and how you derive them. Okay, so I'll then continue. Alright, so remember we were integrating between two positions, point 1 and point 2. Okay, and these terms here have to equal a constant, right? And remember that we are just integrating at two arbitrary points. So let's say I have this one point here, which is close to the free stream. So I have pressure to be P infinity, which is the free stream pressure, and U, the velocity, to be U infinity, which is the free stream velocity. Okay. So according to the Bernoulli's equation, all right, my static pressure plus my dynamic pressure, okay, is going to be equal to, all right, the static pressure at this point here, okay, plus the dynamic pressure at that corresponding point. And you can see that these 2 points does not have to lie along the same streamline. It could be anywhere in the field. All right, so this point which I've taken, it's along my half Rankine body. Okay, so I want to find out what's the pressure difference between the pressure at the surface, on the surface, relative to my free stream pressure. So I'm just going to rewrite that. So I'm going to have P minus P infinity equals to half rho, okay, and bracket U infinity squared minus U squared minus V squared. Okay, so I'm just rearranging my Bernoulli's equation. Right, so it's useful to express this pressure difference in terms of my pressure coefficient. Okay, so pressure coefficient, hopefully you all know, is just that it's just my pressure difference normalized by the dynamic pressure, okay, of the free stream, right? So it's normalized by half rho U infinity squared. Okay. So I'm going to substitute that expression into P minus P infinity. Okay, so I'll get something that looks like this, right? So just keep in mind that the density terms cancels off. So does the half term as well, cancels off. So I end up with Cp equals to U infinity squared minus U squared minus V squared. Divide the whole thing by U infinity squared. Okay. Or Cp equals to 1 minus U squared plus V squared divided by U infinity squared. Right, now I can express this Cp, or I want to express Cp as a function of x, right, along the surface of my half Rankine body or along my separatrix. Okay, so to do that, I'm going to substitute my velocities u and v. Okay, so I know the velocities u and v along my separatrix. Sorry, this is the velocity along in the flow field, right? So from my stream function, I got these velocities. Okay, and I'm going to substitute u and v back into here. Okay, so you can see it's going to be a bit messy. If you expand these terms, okay, it's quite big, but don't worry too much. So you can take out this term, right? So you have u infinity squared over u infinity squared. Okay, so you get 1 and you end up with 1 minus 1. Oops. Okay, so you end up with 1 minus 1, right? This term here, I'm just taking it out, so I get a term that looks like this. Okay, and I'm combining these two terms here to form the last term which I have here. Okay, so you can see that x squared plus y squared, I can cancel one of them, right? And oops. Okay, and in this case, well, if you look back at your lecture notes, exercise 5.2, we have assumed that the strength of our source relative to our free stream velocity is 1. Okay, so all I can do then, I can substitute this with 2, and this term here is 1. Okay, it's just 1 squared, basically. Right, and I get my pressure coefficient to be a function of x and y, which is good. Okay, so this tells me my pressure coefficient at everywhere in my flow field, right, at all x and y locations. Okay, but we are not interested in the pressure coefficient at everywhere. All right, we are only interested in the pressure coefficient along the surface of our half Rankine body, okay, which is along our separatrix. Okay, so we know what's the equation of a separatrix. Okay, it's just this equation here. So all I have to do then is just substitute this back into my equation for Cp. Okay, and by the way, this equation here becomes y cot y because that's just equals to 1. Okay. Right, so I can then substitute x with y cotangent y. Okay. Right, so I can express my pressure coefficient just as a function of y. Right, so if I look at the pressure distribution along the positive y, okay, where x is just equals to y cotangent y, okay, I'll get a pressure coefficient distribution which looks something like this. Okay. Right, and this is something which you can easily do, all right, in MATLAB. Okay, so remember, all we have done is we have just substitute. So remember that your pressure coefficient is just your pressure difference, right? Your pressure difference with the free stream normalized by the dynamic pressure of the free stream. Okay, and the pressure difference we obtain, right? P minus P infinity, that's from our Bernoulli's equation, right? Okay, and then we get it in terms of velocities, Cp in terms of velocities, okay, but then using your stream function, okay, you can then express your velocities u and v in terms of x and y. Okay, and as I'm interested in the pressure distribution along the separatrix, I then substitute the equation of a separatrix into Cp. Okay, that's how I got this plot here. Right, so hopefully you all can see that it's symmetrical along the x-axis. Okay, so my pressure distribution along the half Rankine body looks something like this. Okay, and I have pressure, or the arrows are pointing inwards of my solid body, which means that there is high pressure, or the pressure coefficient is high there, right? And these arrows are pointing away from my solid body, which means that those regions are regions of low pressure. Okay. Right. So if I plot my velocity contours, hopefully you can see that here at the leading edge of my half Rankine body, it's a stagnation point, so my velocity is 0. Okay, and hopefully you can see that that's why I have very high pressure coefficients at the front, right? Because it's all static pressure. Okay, and at the side of my half Rankine body here, the flow is quite fast, right? That's why my static pressure is quite low. My dynamic pressure is high in this region, but my dynamic pressure is high, but my static pressure here is low, and I have very low pressure coefficients there. Okay. Any questions? Yep. Sorry? The pressure, no, so this is velocity. So we are looking at velocity contours. So the lines, this blue line here, only that is your pressure coefficient that we're looking at. Yeah, but the background, that's just velocity. Okay, and hopefully from Bernoulli's, you know that if you know the velocities, you can kind of know what the pressure is as well. Right? Yeah. Yep.
We don't have flow inside the solid line, right?
You have flow inside the solid line. You have. But we are not interested in that, because we have replaced it with our solid body. We've replaced it with some solid body, right? So there's some flow, right? It's going to be moving to the left, but it's not of interest.
That's why we included it in the u velocity, u infinity plus the source. The velocity.
U which?
Yes, this one.
This one?
Minus u plus qs.
Yep. So that's just from our stream function. So my stream function, I just differentiate psi with respect to.
Yeah, I know.
Yep.
But I thought because we have solid, now we don't have flow inside. That's why.
Technically, we still have flow inside, but we don't care. Yeah, because we've just replaced it with a solid body. So we are, the region of interest is everywhere outside of the solid body, basically. Yeah. Okay. Right. So I think that's all for today, and we'll continue on Wednesday. Right.
Why is the velocity so low here?
It's a stagnation point, right?
Yeah. Oh yeah. But
maximum velocity.
So shouldn't be higher, shouldn't be very high near the source and
Source and, well, not necessarily, right? Because you have a uniform flow now, and then you have a source. So your uniform flow is causing the source to.
so it won't be higher, the velocity won't be higher near the source.
Not necessarily, right? In this case, the velocity is high around here, right? Yeah. Because the flow is going around the body, so it has to accelerate here. Right? That's why it's faster. Yeah. Yep. So it can be pi or this term here approaches pi or negative pi, right? So that's why it is plus minus this term here. It cannot be this term approaches 0.
But this way, why is this not minus pi?
Yeah, so this is minus pi. So, sorry, this is pi. So you get y equals to plus qs over 2 in
Yeah, so for the minus pi, so the y is the minus.
negative. Yeah, I didn't do that part. But yeah, that's correct. Yeah.
For the practical one is the practical.
So if you go to click one of them,
Okay, just give one.
yeah, one of, if you just click this now, you open something. Yep. Okay. So you see, right? This one it says engineering block B Parkville, right? So this one is your F4 lab
I feel that.
because it doesn't tell you the room. Yeah. But this one, sorry, this is F4 lab. Department organized venue is your F4 lab.
Okay, so this
Yep.
one is okay. So
Prep 1 is your EDS, which is, it should be an EDS, right? You didn't see EDS? Let's see.
Yeah, I think it does.
It should say EDS,
It's
right?
ADS 5, I think.
Yeah. It should, so it should be your MATLAB workshop.
MATLAB workshop.
Yes.
Okay. So I have to turn to this one
Yes.
with my teammates or
Well, whoever who registered. So,
okay.
yeah, so this one is 13 August, right? So that is tomorrow.
Yeah.
So yours is tomorrow.
okay. Alright, thank you.
Okay, no problem. Hey,
Just quickly, the Bernoulli's, that's only at constant height because you don't have the GH term.
Oh, we have ignored gravity, I guess.
Yeah.
So it's, there's no gravity.
So are you looking at constant height? Because like if you obviously have a flow that's got height, then it'll be.
Well, yeah, I guess it's idealized. So if you don't have gravity,
Yeah.
so then it can be anywhere. Yeah. Alright, okay. Oh, so because when it's irrotational, right? We can substitute this equation here. Right, and that's valid everywhere. You don't have to integrate it along a streamline or anything. It's everywhere. Yeah. Okay. Right.
So today I got this email saying that
Right.
there are 2 Wednesday sessions that have been added. So I signed up for one of the Wednesday sessions.
Okay.
But how do I know which Wednesday session is that? Because one of them is this Wednesday and one is on the 28th. But this email does not say which one is this Wednesday.
Did you sign up for Wednesday 28 or did you sign up for Wednesday 14?
So the name of the practical one is, it is just Prac 2 27. There's no date given on that.
Are you sure?
Yeah, that's
On the
timetable. Yeah. And also had doubts regarding the assignment. I just opened the assignment, I went through the assignment.
Okay. Yep.
So there are certain questions which ask for the derivation. Regarding the derivation, do we write it down, we scan it, or the derivation has to be typed on board?
Yeah. I think typing would be good.
Typing on board?
Typing.
Okay.
Yeah, typing.
Okay. And secondly, there are questions also for just solving, integrating the analytical solutions for certain equations, normal equations. So for analytical equations, we don't have to write a word program. That will only be for Euler's and Ranjakutta.
Yes.
Yeah. So analytical is pure derivation, right?
Yep. So you should be able to integrate.
Integrate, yeah. So no programming for that.
Don't think so. Yeah, I don't think so.
Okay. This is the one.
Yep.
It just says practical to 27.
Okay. If you click that, it should tell you your date.
No, it's
Can
not.
open? Can you open it?
No, that's nothing.
No, sir, because
That's
we
it.
just received a
So that's what I don't know which one it is.
So we just received a mail with a list
So it
of
just
that.
says that
Tuesday, Wednesday. So I don't know which Wednesday that one is.